Welcome to Pass Academy. In this video, we are going to look at the introduction to organic chemistry, hydrocarbons, and the various functional groups in organic chemistry. So let's talk about hydrocarbons. Hydrocarbons are organic chemical compounds made entirely of carbon and hydrogen atoms. Carbon atoms form the backbone of hydrocarbons. So why carbon atoms? When we look at the hybridization of the carbon atom, it forms 4 sp3 hybridized orbitals, and then it uses these sp3 hybridized orbitals to form other bonds with other atoms. So we can form a carbon to carbon bond with another carbon, and then these carbons can form other bonds with, let's say, hydrogen, and then we can also have other atoms such as bromine and hydrogen. We can also have chlorine here, and then hydrogen atoms bonding with these carbons. So from our structure here, we can see that this hydrocarbon is made up of what? These carbon atoms, let's say carbon 1 and carbon 2, and then hydrogen atoms. We can see it is made up mostly of hydrogen atoms and then the carbon atoms. So let's continue. Let's move on to functional groups. Functional groups are small groups of compounds that exhibit similar characteristic reactivity. What do we mean by this? It means if we combine one set of functional group to another functional group, the functional groups, when they react with other compounds, they exhibit almost similar reactivity. So what do we mean by this? It means when we take one compound in a functional group and then we react these compounds with other chemical compounds, the products they form exhibit similar properties. So let's move on to the first functional group. We have alkenes. Alkenes are the simplest and saturated hydrocarbons, and they have single carbon to carbon bonds in their straight chains. What do we mean by this? It means when we look at a carbon atom, where we say it forms 4 sp3 hybridized orbitals. These orbitals bond with other atoms, for instance hydrogen, and in alkenes we said it is made up of single bonds, and so these 4 sp3 hybridized orbitals, as we can see here, have formed the maximum number of bonds they can form, and so therefore we can't add any other atom to this compound, therefore making it saturated. We can also have other forms. We have the carbon atom being bonded to another carbon atom, and then we can have hydrogen atoms here. We can even have halogens bonded to our carbon atoms. We can have a halogen, for instance bromine, and then we can have a hydrogen here, another hydrogen bonded to this, and then another hydrogen bonded to this. So from here we can see that these carbon atoms, carbon 1 and carbon 2, have formed the maximum number of bonds they can form. Let's see. This carbon atom, carbon 1, forms 1, 2, 3, and 4 bonds. Likewise, in carbon 2, we can have 1, 2, 3, and 4 bonds. So the carbon atoms have formed the maximum number of bonds they can form, therefore making this hydrocarbon, which is an alkane saturated in nature. Let's move on to the next functional group. We have alkenes. We say the alkenes are less saturated compared to the alkanes, and they have double carbon to carbon bonds in their straight chains. So in alkenes, when we look at, let's take the hybridization of a carbon atom. So we have this carbon atom, and then it forms a double bond with another carbon atom. So this carbon atom having an electron here and this having an electron here will lie side by side with this carbon atom, forming a pi bond, and then this hybridized orbitals having their electrons here will lie head on to form a sigma bond. So this gives us an alkene which have double bonds between the carbon atoms, and then these other orbitals can form bonds with other atoms, in this case hydrogen. So if you look at this carbon, let's say carbon 1, we can see that it has formed the maximum number of bonds it can form in this compound. This is bond number 1, bond number 2, bond number 3, bond number 4. Likewise, if you go to the other carbon, carbon 2, we can see it has formed bond number 1 here, 2, 3, 4. So pi bonds are formed when the hybridized orbitals lie side by side, and then sigma bonds are formed when the hybridized orbitals are bonded head-on. Let's move on to the next functional group. So looking at alkynes, and then they are the least saturated hydrocarbons. They have triple carbon to carbon bonds in their straight chain. So likewise, in the alkynes, we look at the hybridization of the carbon atom. So it forms 4 sp3 hybridized orbitals. So we have another carbon here forming a head-on bond with this. So this hybridized orbital will lie side by side with this to form a pi bond, and these ones collide head-on to form a sigma bond, and this also lie side by side to form a pi bond. So we'll be left with one hybridized orbital here, which it can use to form bonds with other organic atoms, and then another here. So we can see that the carbon atom here, carbon 1, has formed the maximum number of bonds it can contain. It has bond number 1 here, bond number 2, 3, and then 4. And then when we come to carbon 2, we have bond number 1, 2, 3, and 4. So why do we say this hydrocarbon is less saturated? Because when we react this hydrocarbon with other compounds, these bonds can break to form bonds with other atoms for this hydrocarbon to be saturated. Let's move on to the next functional group. We have halides. Halides are formed when an alkane straight chain is single bonded to at least a halogen. So we know our halogens. We have fluorine, we have chlorine, we have bromine, and iodine. So these halogens form bonds, at least a single bond with a straight chain alkane. So we know alkanes have single bonds. So if these carbon atoms in the alkene form at least one single bond with any of these halogens, then we say we have a halide. So in this case, we can have this carbon atom being bonded to a bromine, and then this bonded to hydrogen. We have another hydrogen here, and then this way. We can also have, since we have the keyword at least here, it means we can have more than one halogen being bonded to the alkane chain. We can have the same kind of halogen being bonded to the chain, or we can have two different halogen being bonded to the straight chain. So we can take an example here. So we can have a bromine being bonded here, and then we can also have a chlorine here. Likewise, we can have this, a bromine here, and another bromine here. So in all, we can see that the straight chain alkene forms a single bond with a halogen, making our compound a halide. Let's move on to the next functional group. We have alcohols. And then we say that alcohols are formed when a hydrocarbon is single bonded to an OH group. So what do we mean by this? It means our hydrocarbon from alkane, alkenes, and alkynes form a single bond with an OH group. So we can have, in this case, an alkane being bonded to an OH group. So this gives us an alcohol. We can also have an alkene being bonded to an OH group. So this also gives us an alcohol. Let's move on to the next functional group. We have ethers. They are formed when a central oxygen atom is bonded to two carbon atoms. So we can have the central oxygen atom with two lone pairs being bonded to two carbon atoms. So this gives us a ketone, an ether. So we can have another form of ether. We have central oxygen atom being bonded to two carbon atoms. So over here we have one carbon atom here, another here. So we can see this central oxygen atom being bonded to these two carbon atoms, making this an ether. Let's move on to the next functional group. We have amines. So the amines are formed when a nitrogen atom is single bonded to a carbon atom and two hydrogen atoms. So what we mean by this is we can have a carbon atom being bonded to a nitrogen atom and the nitrogen atom being bonded to two other hydrogen atoms. So this gives us an amine. Let's move on to carbonyl containing functional groups. So these are functional groups that contain a carbon to oxygen double bond. So it means in their bonds we have a carbon to oxygen double bond being bonded to our hydrocarbon. So the first functional group under the carbonyl containing functional groups are the aldehydes. They are formed when the carbonyl carbon is bonded to one carbon atoms. What do we mean by this? We know this to be our carbonyl functional group, and then the C here, the carbon here, is our carbonyl carbon. So this is our carbonyl carbon, and then we said aldehydes are formed when this carbonyl carbon is bonded to a carbon, a single carbon. So this gives us an aldehyde. Let's move on to the next one, ketones. We say the ketones are formed when the carbonyl carbon is bonded to two other carbon atoms. So our carbonyl carbon being bonded to two other carbon atoms. So this gives us a ketone. And then we have carboxylic acids, and they are formed when the carbonyl carbon is bonded to an OH group. So we have our carbonyl carbon being bonded to an OH group. So you can have something like this, with this being carbonyl carbon. This brings us to the end of the introductory video. Meet us in the next video for exciting educational content.